so this is basically a glimpse of how you derive a scheme in finite difference and how to analyze the error of the approximation. So the final topic we want to discuss about actually about this particular equation, but it's actually a general question you want to ask for any numerical solution of any system, not just PDEs, is that once you're committed to some error, what's the effect of that error? Right? How much damage does that error cause? This is because we are not just interested in the second order derivative. I mean, if what we are interested in is just computing the second order derivative of something, then it's fine. We already know how much error we have, right? So once we have the function, we can find some way to figure out the magnitude of the fourth order derivative. We also know our delta x. We know how much error it is. But that's not what we're interested in. We are interested in solving this equation. That's the equation we wanted to solve, right? And by replacing this with something else, right? Something that is a good approximation, but actually not entirely. We are approximating this with, we are converting this to dwi dt, right? That the derivative of the function at a particular grid point is equal to the same kappa times our approximation. If we do that approximation, well, it's good because instead of a partial differential equation, what do we get? We get ODEs. I mean, not just a single ODE. In the previous case, well, if I look at this case, we have 10 grid points, right? The case we have 10 grid points, we have reduced the system into how many ODEs? 10? Do we have 10 ODE here? No. We only have 8 ODEs, right? Because this approximation only works for I equal to 2, etc. to n minus 1, right? So we have n minus 2 ODEs or 8 ODEs. How many unknowns do we have? Well, if you look at the face value, we have actually 10 unknowns. All the W's are unknowns, right? So we can't solve it. We have more unknowns than equations, right? That's not obvious from the PDE, right? From the PDE, the unknown is a function, right? The PDE is also a PDE, so it's kind of the same equation governed. They are all infinite dimensional, but as soon as we reduce it into ODE, we find something interesting. We have less equations than unknowns. What do we do? Boundary conditions, right. So that's something actually I find intriguing. It's very hard for mathematicians to figure out that you need boundary conditions for the PDEs. Is actually a pretty, it's a non-trivial analysis to do that, right? To figure out you only have unique solutions if you provide both boundary conditions for this heat equation. But as soon as you reduce it with finite difference into a finite difference approximation, it's obvious you need 2 boundary conditions from both sides in order for you to solve this equation. You have to know, so for the analytical PDE, you have to give 2 boundary conditions. You have to know what W0 is. So W0 as a function of t, you have to know W1 is as a function of t, or they don't have to be 0 and 1. They can be, for example, in our previous case, it can be -3 and +3. Let's just call it left and right, right? So you have to know these 2 functions in advance for you to even be able to solve this equation. So that means our W1 and the Wn are given. So if they're given, we have 8 unknowns, 8 equations. Or we have 8 unknown functions of time, and we have 8 ODEs. Yes?
You have to give the time conditions at the extremes, or can it be any?
So the question is, do you have to have the boundary conditions at 2 extremes, or they can be anywhere? What do you think? That's a good question. Yes?
The way we discretized here, we don't have an equation for the left and right hand side, so that's why we have to apply the boundary conditions there, because they are the unknowns.
That's right. So it has to be on the 2 extremes. Otherwise, you have duplicate equations for the ones for the boundary condition you provide in the middle, and you don't have an equation for the one at the end. Right? So for equation to be solvable, you have to have the same number of unknowns and equations. You also have to have the equations being independent. Right? Here, if you provide the boundary condition at the middle, you don't have independent equations to solve. You have kind of duplicate, you have conflicting equations. You have conflicting conditions for one of the variables. All right. So yeah, for analytical PDE, you also can prove that you have to have the solution. You have to have the boundary conditions at the end. All right. So the question is, how much error does my approximation bring to the solution W, right? Okay, so let's actually try it again in MATLAB. Let's close everything, and let's see what should we use to compare. For what function do we know some analytical solution that is going to give us a good basis of comparison? Remember what we did in lecture 1? We did Fourier series, right? For Fourier series, we know exactly what the function what the function is like. And for Fourier series, we have to modify the boundary condition a little bit and say that the solution W at the left hand is equal to the solution at right hand, and the solution at the right hand is also equal to the solution at the left hand, right? So that's also 2 boundary conditions you can provide to the system. So when that happens, for the periodic boundary condition, it's a little bit different, because if you have n grid points, one of the grid points is actually redundant, right? So you shouldn't say, so the very left point is actually equal to the very right point. So you don't really have n grid points. You don't really have n independent unknowns. You only have n minus 1 independent unknowns. In addition, you have one more equation, because even for the very end, you know actually what is the value at the left and at the right. You just go to the other side of the domain and look for its neighboring value, right? Because the very first grid point is actually equal to the very last grid point. So if I have a function that is periodic, for this point, first of all, I have one less variable because they duplicate. And also for the same point, I both know its right value and its left value, right? They're just at the 2 different ends of the domain. So I have, for periodic boundary condition, I have one less variable and one more equation. So that also makes up for the number of unknowns and equations. Right? Make sense?